last time we derived the Thomas Fermi approximation to get the Coulomb screening, but that's just a semi-classical treatment. And I also mentioned that the correct language to describe this Coulomb interacting electron gas should be based on this cartoon picture that the electron density fluctuates respect to the average density, and that's small fluctuations serve as a small perturbation in our Hamiltonian. So we should reorganize all these terms in our Hamiltonian and re-express this Hamiltonian in terms of the density of electrons. And so speaking of the density of electrons, so we know very well that this is nothing but counting the electron number, right? So we know for sure that from our original definition of the electron operator, say in momentum space, we define C diagram of K and C of K, and the number of electrons in momentum space, remember, is defined as C diagram K of CK. And we also define the creation destruction operator of an electron in real space, defined by this psi diagram of R and psi of R. So we have both creation destruction operators defined in K space and real space, and they are related by this Fourier transformation. And this transformation guarantee that in both spaces that the anti-commutation rules are satisfied. And this is also one of your homework problems to show that this anti-commutation rules for fermion operators in real space is given by this Dirac delta function. So now you could imagine that we could define in a similar way, like in momentum space, the electron number operator or density of electron in real space, which is given by simply just psi diagram R, psi of R, which is indeed the case. So if we consider the real space representation of the two-body interaction, such as the Coulomb interaction, and we already defined this, the Coulomb interactions, and this is given by, say, two incoming electrons to be destroyed, and then two outgoing electron states to be created, and at different real space locations R and R prime, so they interact by Coulomb. And so we could sort of define this electron density in two ways. First, we simply just count the particle number, right? So suppose this is the distribution of electron, and to count them without using the second quantization, we simply just count how many, say, points, point charge particles are there in the real space. So each one of the point charge is defined by the delta function, right? Okay, so you simply just sum over all bunch of delta function, a Dirac delta function, okay? But this sum over the Dirac delta function in real space could be rewritten in terms of this kind of an integral, and also sum over all this point charge. But inside the integral, you could just insert this psi diagram of R, psi of R, and to the left and right side of the Dirac delta function, and you could get this kind of summation, psi diagram of Ri, psi of Ri, which is nothing but a rho of I, right? So if you consider this electron are these free electrons, so their wave functions are just the plane waves, and this is precisely what you'll get, the plane wave. You sum over all this, psi diagram, psi, where psi and psi diagram are just plane waves, and then you simply get this bunch of delta function to be summed over. So therefore, we can second quantize this electron number operator or density operator in this way that we could count them. Okay, we sum over all such electron distributed in real space, and that will be all. But of course, we need to re-express the Hamiltonian in terms of psi dagger Ri and psi of Ri. But then we should also express this in terms of electron density operator, both in real space and also in momentum space. Okay, so this is what we should do, because we know that depending on what we are going to calculate, in some cases it is more convenient to define the Hamiltonian in K-space, but sometimes it is more convenient to define the Hamiltonian in real space. Of course, for the weakly Coulomb interacting electron gas, it is more convenient to define the electron operators in K-space, because we know this, these diagrams that two electrons exchange the momentum Q when they get scattered, and those electron states are very close to the Fermi surface. Okay, but of course we need to go step by step. So the first is that we study a little bit more the Fourier transform of this electron density operator. So it looks trivial, but it's not trivial at all. Why? Because precisely of the fact that they are related by the Fourier transform, this C dagger K and psi dagger R. And if you Fourier transform this density operator, you will find that there are two momentum to be taken care of. So let's Fourier transform this. So I use Q to represent this, say, Fourier component of the electron density operator in K-space. And this is given by, again, you simply just Fourier transform the electron number operator in real space, following the standard definition of a Fourier transformation, and you will perform such integration over real space dr with the Fourier coefficient e to the minus iq dot r. But what is this rho of r here? A rho of r is defined precisely by this, say, psi dagger of r psi r. But what is psi dagger and psi? Well, they are related by the C and C dagger. Okay, so now you could plug in this relation. You'll get this, and then double Fourier integral, right? Okay, you simply just plug in the Fourier transformation of psi dagger and psi, and you transform these two operators from real space to momentum space, and you try to define this Fourier transform density operator, and we could clean up the notation. Delta function, the Kronecker delta function, if you sum over the real space variable dr. So if you sum over or integrate over dr, you will get the Kronecker delta function, because you could combine all these terms, e to the minus iqr times e to the I k prime minus k dotted r. So this will be e to the I k prime minus k minus q dotted r, right? So if you integrate over the r, you'll get the Kronecker delta function, delta k prime minus k minus q, which is precisely this Kronecker delta function written here, so that now this summation vanishes if k prime is not equal to k plus q, but it is, say, the delta function equals to 1 if these two momentum variables are the same. Okay, and therefore we could immediately get rid of one of the summations, say k prime. So you'll get 1 over v and sum over k and C dagger K and C K prime. But K prime now should be replaced by K plus Q. And this is supposed to be the Fourier component of the density operators and as function of momentum transfer Q. Well, this is different from the N of K over here that you simply just count the electron number in momentum space. Okay, because this is C dagger K of CK, but the electron density operator in momentum space is not C dagger K CK, but C dagger K CK plus Q. Okay, so there is a plus Q, and you sum over all possible K, and you get the Q component of the density of electrons in momentum space. Okay, so it looks similar, but it's not exactly the same, and there's a tricky difference between electron number operator, C dagger K CK, and also electron density operator in Q space. But they are closely related to each other. So if we forget about this Q, or Q is 0, then rho of 0 component is nothing but the electron, total number of electron, right? So if this Q equals 0 limit, this is nothing but sum over K, C dagger K CK, which is sum over K, N of K, which is total number of electron, right? So we have mentioned that many, many times in the past. So there is a close relation between rho of Q and N of K, right? Okay. So let's take a short break. When we come back, we will continue expressing the Hamiltonian in terms of rho of Q. So I believe these definitions are pretty standard. You could find this definition anywhere in Flansburgh, in Kittel's second book, and all the other, or David Pine's lecture notes. So let's continue. Rho of Q, and you could also shift this momentum, because this momentum is actually a dummy variable, or you could simply just shift this momentum K to K prime minus Q. And therefore, rho of Q could be also expressed in terms of K prime, like this. So either way, it doesn't matter which convention you like. Okay? So let's just look at the physical interpretation of such an operator. So it looks like you destroyed a particle of electron carrying momentum K plus Q, and you create another electron at momentum K, and you sum over all possible that processes over K. What does that mean? Well, if you look at the real space representation of the electron density operator, so this has a very easy interpretation, meaning you simply just destroy the electron here at location R, and you created the electron again. So therefore, you count the particle number at real space vector R. But what does this rho of Q refers to? As I mentioned, it looks like it's not the single processes that it refers to, but it is the sum over all such processes. Okay, so it tells us that you need to first destroy the electron occupied state at momentum K, and then you create another electron, most likely the out of the Fermi surface, carrying momentum K minus Q, where Q could be either positive or negative, and you sum over all such processes, which means that you have this processes and all the other processes, and you sum over all such processes. Okay, so what does that mean? So remember when we first introduced the concept of the quasi-particle, and this is quasi-particle, right? This is electron hole pair. So rho of Q effectively sum over all such electron hole pair production and over the whole say, occupied states. Okay, so it means that you create particle-Hall pair. But you do not just create one, but you create many. And you take the average in some sense, right? You take the average of particle-Hall pairs and you sum over all possible such a particle-Hall pair. And we will see later that the rho of Q is closely related to this kind of electron-hole pair excitations. And later that this screening of Coulomb interactions should be understood in terms of this rho. So let's just try to represent this Hamiltonian of a Coulomb interacting electron gas in terms of rho of K or rho of Q. This is what we had before, right? So we had that before when we defined the Hartree-Fock, right? So this is one step before, say, we treat this Hamiltonian in a Hartree-Fock way. So it is the Coulomb interacting electron gas that we defined already. But now here comes the trick. So remember, in Hartree-Fock, we have not defined this rho of R or rho of Q when we deal with the Hartree-Fock. So we just keep this 4 fermion term as it is when we perform this Hartree-Fock approximation. But now this is different. Okay, so we need to re-express this 4 fermion term in terms of the rho of Q and see how we can achieve this. Right? So by first sight, you see that this 4 fermion term looks very similar to the term that if I simply just do this. Because, for example, if I consider this term, C dagger K minus Q, CK, this looks very much similar to rho of Q, right? And we need to sum over K. And this middle two operators looks very similar to rho minus Q, right? You sum over K prime. So this already tells you that this 4 fermion term could be expressed in terms of a rho of Q or rho of minus Q. But of course, we need to take care of this anti-commutation rules more carefully. Let's do it. So we just focus on this 4 fermion term, which is rewritten with the help of the anti-commutation relations. So you first exchange the C dagger K prime plus Q and CK prime, and you could rewrite this in terms of the CK C dagger K prime plus Q, and by using this anti-commutation rules, right? Okay. Then you could simply just expand all this term. C dagger K, and plus sum over K prime minus Q, CK, dagger K prime plus Q, CK prime. Okay, so I need to convert these 4 operators in the proper order when I try to represent this term in terms of the rho, because the rho operator is in the form of C dagger C. So I should also do the same. So the first 2 operators, C dagger K minus K, CK, you sum over K. This is nothing but rho of Q, right? And the second term, you sum over K prime, C dagger K prime plus Q, CK prime. This is nothing but rho of minus Q, right? But you have the leftover. The constant term, the delta function, gives you an extra term, which is minus sum over K prime, C dagger K prime, CK prime. So then you should just combine everything. So this is minus sum over K prime and K prime plus rho of Q times rho of minus Q. So you can see that we're almost done. Okay, so this is a Coulomb term which comes from this definition. So the Coulomb interaction could be re-expressed in terms of the density-density interaction. Okay, so if you look at this term, rho of Q times rho of minus Q, you immediately recognize that, okay, so this is just a density-density interaction that you are familiar with in the classical electrodynamics, right? So the Coulomb interaction is nothing but, the density-density interaction between two charged particles. So this constant term is just a shift of your Coulomb term, and it doesn't affect much. So we know that this density operator is actually Hermitian operator because it actually reports the number density of electrons, which is for sure a real value, and therefore the second quantized operator for the electron density should be Hermitian, because any Hermitian operator gives you the real eigenvalue, and therefore this rho dagger of R is the same as rho of R. And from that, you can immediately see that this identity holds. Rho minus Q is nothing but rho dagger of Q. So I leave this to you as a homework exercise. It's really simple, just one line. You can show that if you take the dagger of the rho of Q, it's the same as if you replace Q by minus Q. It's the same thing. Okay, so with that identity, you could summarize this Coulomb interacting electron gas in terms of the density operator, where capital N refers to the number of electrons coming from this term here. So this minus N number of electrons. So this is a very important equation that we successfully re-express the Coulomb interacting electron gas, the Hamiltonian of this system, from this full fermion operator form to the rho dagger of rho and minus a shift. So now we are in a position to study quantum mechanically fluctuation of the density operator by studying the time dependence of the density of your electron operator in the Hamiltonian. As I mentioned, we have this small density fluctuations both in real space in a time domain. So that electron density operator fluctuates back and forth both in the axis of the x real space or in the time domain. And we will simultaneously capture this kind of features so that we can understand the screening of a Coulomb potential, and this language is the correct language to study this screening of a Coulomb potential and also study the plasma oscillations, which is nothing but the periodic oscillations of electron density in solids or plasma. Okay, so in other words, this Hamiltonian is the correct starting point to capture both the screening of electron interaction and also the density fluctuations in ordinary metals. So it's just some mathematical manipulations, but we will address in more details the physical interpretation of such electron pair excitations. And so far it's just a single electron hole pair excitations, but later we will see that this rho of Q is actually a periodic function in time. So the density of electrons actually fluctuate back and forth, and it undergoes the high frequency oscillations with the frequency omega c called the plasma oscillation frequency, meaning all the electrons are dancing together in the same frequency. So we will differentiate the single electron hole pair excitations from this collective motion of electron density operator. It's a collective motion of electron density, and which leads to so-called plasma oscillation. And when we study the screening of a Coulomb potential, we will simultaneously derive such a plasma oscillation frequency and also linked to the single electron hole pair excitations. Okay? So the plasma oscillations are very interesting phenomena in solid state, especially in ordinary metals. When you hit this metal thin film by electrons, you will see the, say, scattered electron shows some periodic modulations as a function of your energy. And then that period or frequency corresponds to precisely the plasma oscillation frequency, meaning all the electrons move in a time domain in the same manner, so that you will see this phenomena as a macroscopic phenomena, not a microscopic phenomena. Okay, so that's a very important point. Okay, so I guess that's probably enough for today. So let me just tell you what we will do on Wednesday. So on Wednesday, we will again study what kind of operators that will lead to such a single electron hole pair excitations, and what kind of operator that lead to this collective motion, plasma oscillations, and what is the equation motion for this density operator, rho of Q. So we will use this Heisenberg equation motion method to calculate the time dependence of this density operator in K-space, and we will try to find out this kind of density oscillations, especially this plasma oscillation frequency. So we will try to solve this Heisenberg equation motion for this rho of Q, but it's not that straightforward job, because the first order of a Heisenberg equation motion, you get nothing. Okay, so you will not get this oscillation frequency by solving just the first order Heisenberg equation motion for rho. So we must continue to actually get to this periodic motion by the second time derivative of rho, meaning we need to solve the double commutator from the Heisenberg equation motion, and from that we also need to make some approximations. And under some approximations and second time derivative of the rho operator within the Heisenberg equation motion, and we are able to get this omega c. And we also can understand how this Coulomb screening effect come about from purely quantum mechanical treatment. Okay, so I guess that's enough for today. Okay, so you could play these operators at home and convince yourself that this Hamiltonian is the correct expression. So one more remark. So as I mentioned, in the Hartree-Fock language, there's no correlations between spin up electrons and spin down electron, right? So either all the spins in the Coulomb scattering are all pointing up or all pointing down. Remember that, right? In the Hartree-Fock, we have only two possibilities, that all four electron states are either pointing up or pointing down. So therefore, this Hartree-Fock theory overestimates the importance of a ferromagnetic ordering. Okay, but it's not true. There are not so many ferromagnetic materials in nature, and the reason why this Hartree-Fock fails is precisely because the Hamiltonian in the Hartree-Fock language is not written in terms of the density operator, which it should be. And you immediately see that indeed we do have such a, say, interaction between spin up and spin down. Okay, because rho, remember, is the sum over particle hole pairs, right? So, but you could very easily decompose the spin up component and spin down components of rho of Q, because the spin indices are summed over here implicitly, right? So when we say we sum over K, we also imply that we should also sum over spin. Okay, so of course rho of Q is a sum over the upspin component rho of Q and downspin component rho of Q. Okay, so if you have such a rho dagger rho interaction, so immediately you'll find that you have 4 terms, right? Roll up, plus roll up, roll down, plus roll down, roll up, plus roll down, roll down. Yes? Okay? So, of course, the Hartree-Fock only emphasizes the up-up and down-down interactions between electrons and neglect totally the up-down interaction. But here, in the density interactions and the electrons between upspin and downspin species do interact because we have such a term. We have an interaction between upspin species and downspin species. So therefore, it is the correct, physically and mathematically correct form of a Coulomb interacting electron gas, and therefore the Hartree-Fock starting point is totally wrong. Okay, so this form is okay, but when you really do some calculations, you really need to transform the 4 fermion term in terms of density interactions. Otherwise, you are going to miss half of the interactions between upspin species and downspin species. So now you can realize how tricky it is. I come from the same Hamiltonian, but I could get completely different results. If I follow Hartree-Fock and we get the wrong result, if I follow this density interactions, we get correct results. So what is going on? Okay, so this is a very important lesson to all of us studying physics, that even though we start from the same Hamiltonian, depending on how we treat this Hamiltonian, we may have different results. The Hamiltonian is the same, but our approaches are different, and therefore we may end up with different results. You may say that, well, why not we simply just solve this Hamiltonian and solve the eigenvalues and eigenenergies exactly? Well, forget about this. At the beginning of the lecture, I mentioned it is not possible to solve the general equation for that 10 to the 23rd that many atoms electrons for the first place. And therefore, everything follows, of course, needs some approximations. Okay? But the crucial thing is that we need to make a reasonable approximation. Okay? And we should avoid some really dangerous approximation which will actually turn out to be troublesome or give us some misleading results, like Hartree-Fock. So now you could really realize that this is a more reliable starting point. So later we still make some approximations based on this form, but these approximations under reasonable assumptions will give us a very good results compared to the experiments. Okay? And the density fluctuations or small perturbations are there indeed small perturbations. And everything follows. Okay, so I should stop here and let's continue on Wednesday to study the equation motion for electron density operator in Q space. Okay, so I recommend that you need to get familiarized with the notations and the relation between the electron hole pair and the number density. Okay, and try to derive all this equation by yourself, and then you will appreciate the beauty of this solid state physics.